Hi everyone, and welcome to the section 5.4 study guide, lecture, however you want to think of them. So for each section, there's going to be one of these documents that you can find on Blackboard. And then what I'll do is I'll make a video. This first video I'll go through a lot more detail on the beginning and kind of skip it for the later videos since it's all going to be very similar. But basically, you can use this plus the other resources I give you as like your replacement for the lecture, since this is an asynchronous course. As I've discussed in previous videos, like the class intro video, I'm still going to be having consistent office hours where you can email me, meet with me via Zoom. But I'm also happy to do things outside of those. You just have to let me know when you're available and we can go over any issues you're having. So the structure of this then will be, this is trying to give you a general idea of what you should be focusing on, because I'm going to give you lots of resources. The book is quite thick. There's lots in it. There's lots of examples. So this is about trying to help you focus a little bit on what you should have as your priority as you're studying. And then you can use the other resources as you need, right? And so the way this is going to go is there are some general guidelines here. First things first, the textbook is, besides this, and this is really an offshoot of the textbook, your main resource. So you've got to be reading through the textbook. This is a math textbook, so just like other science classes you've had, the reading of this is different than reading in other courses or just leisurely reading, right? You have to do it differently. You have to be engaged with it, okay? It is nice if you have taken it upon yourself to check out the section and some of the material before doing the video. That's always helpful because, you know, just kind of getting it multiple times is good, but especially with the terminology, if there's new terms, the more you see it, the better. So instead of me having to introduce a new term, if you've seen it already, then, you know, you're not going to have to stop the video quite as many times. You're going to be able to kind of just listen a little bit more, actively listening, instead of having to take as many notes, things like that, and that's just beneficial. Right? And that extends to taking classes in person synchronously as well. I highly recommend for your other courses as you go through your academic career. Find out, which shouldn't be too hard to do, what you're going to do each day. Read ahead. You don't have to understand ahead. Read ahead a little bit, at least so you have the terms down. Try to jot down what the key terms, the new words are, things like that. Then when you go to lecture, you know, if that's the course structure, then you can just sit back a little bit more and listen, deeply listen. And of course still take notes if that's what you want to do, but your focus when you're in class is engagement and not having to worry so much about like, oh, I got to write this definition down, I have to do this new word, because you've already introduced yourself to this. You've got it in your head. The gears are turning a little. So that's a great way to do this as well. The video can be your first thing, but it's often nice to try to skim through a little bit. The last thing I'll say on that, because I'm rambling now, which you'll see me do a lot of, sorry. I should change it. I won't. We're just going to get through it. Is you're going to read through something, I don't really get this. But if you've already done that on your own a little bit, then when you get to the video, you're more likely to have the thing click. I didn't get this in the reading, but we just did this example, or Mr. B said it in a way that, I get it now. And so you can kind of help use the video in these future resources to fill in blanks that you have when you're reading the textbook, which will happen to every single one of us. That's part of the process. So then you go back and you read again, you're like, oh yeah, I remember this from the video or this example. Okay, this is making more sense now. And that process is how you're going to go through the course. So what else is there that you should be looking at? Well, there are videos, extra videos, inside the book as well. I think every section has at least one, where they're pretty helpful. And, you know, they're not going to be a video that covers everything, but they're more specific videos that I think are very useful for you to check out. And so oftentimes in these, there'll be a specific video I want you to watch, and it'll be kind of like make sure you check this video out. There's this key point in here you should be really thinking over. Okay, so those videos aren't necessarily supposed to be everything, but they're just nice additional pieces that I'll point out once in a while that are available in the ebook through WebAssign. So the next thing that will happen for each of these sections is I'm going to point out in the book what examples are. You have got to have this down by test time, quiz time, whatever. So it's not like you got to read this and I don't get it right away, I failed. No. I just want you to focus on these and make sure that by the time we are testing on things, you've got these examples down. And then there's other examples that aren't quite as important. They're still interesting and useful for understanding possibly, but they're not what the focus is. So in this first section, 5.4, examples 1, 2, 3, and 5 are really very important. They're either showing you some mechanical way to solve a problem that you really need to have down, so it's great to just see it done, so you could try replicating that process. Or they're trying to show you something in a different way, or just kind of trying to explain something, okay? So you're going to make sure you go through those examples, you feel confident on them, you're asking me if you're not, okay? Then there are some practice problems in the book itself. Practice, these are, you should be able to solve these after fully understanding, or at least partially understanding, what we do here plus the book, okay? Examples. So how can you kind of use this, right? If you're not really sure how to do this course, what do? You go through the reading, focusing on the examples I've given you to focus on. You can watch this video, and there are timestamps in the, these all go up on YouTube, and so just check the description because there'll be timestamps so that you can jump around here on this video. So you can use this video if you want to use specifically. Like, I didn't really understand this idea. Let me look through this document. Ooh, okay, Mr. B's talking about it here. Let me skip to that. So feel free to watch the whole video as well, of course. But you can use this also to kind of, specifically get at some ideas you're not sure about, right? Okay, but then what should you be doing? And what should you be doing the whole time is here are practice problems, new prompts for you to try. All of these are odd, 3, 7, 9, 13, 19, 25, which means their answers are in the back of the book. So you can check how you're doing. And of course, you can come to me about these and we can talk about them together, of course. So these are practice problems that are little kind of mini litmus tests. Litmus tests. You know what I'm saying. For how you're doing in each idea. So you're going through here, you're reading through the examples, and maybe you're like, okay, I'm feeling okay on this. Immediately, before you even watch the video, try some of these problems. Which ones were you just like, boom, I got it? And which ones were you saying, not quite sure? The ones you're not quite sure about, keep those in the back of your mind. Mark them down, right? Think about where they seem to connect to from the book, right? So that's an important thing to do. We're learning something in the book. Maybe there's a new definition, a theorem, an example, a type of problem. Once you've kind of got a feel for those, you go work on the practice, connect the practice back to those. The things you're not getting, well, that's what you got to go read again. If number 13, is very similar to example 3 and you couldn't get 13, well, you go back to example 3 and make sure you really understand the steps they're taking. And then you come back to this document overall and try to go through and see if we talked through that as well. What example extra I gave that might connect to that practice problem you're getting stuck on. Once you've done that, you go back to the practice problem, try it again. You get it? Great. You're still stuck? That's a perfect time to send me an email with what you've tried, what you're thinking. That's always helpful. Come to an office hour, set up a time to meet. We can go over some of this together. So, hopefully you're seeing that this is not necessarily linear. Right? Learning is not linear. It's not step, 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 step. It's step, step, go back. Try something else. Step, step, go back again. Go to a different resource. That's the way that you're going to be able to progress through this course. All right? So, again, that's a lot to say. Sorry. Just this first time I want to kind of tell you what this looks like. And then in future videos, I won't go so deep into what's kind of happening here. I just want you to know each time, focus on these examples, practice these problems, right? And then in some sections I'll say, okay, this video, you definitely check this out. So let's get into the actual material. It only took me 10 minutes to get through this first chunk. So, section 5.4. We're talking about the fundamental theorem of calculus in this section. But what we have to do is we have to start with this idea of the evaluation theorem. Now, depending on your background in calculus, your Calc 1 background, you may have just played with this a little bit, or you may have done this plus some extra that we're going to kind of go back through anyway. So just so we're all starting on the same page here, the first thing we need to remind ourselves of is this thing called the evaluation theorem, which maybe you've, used this wording, maybe not. It's okay if, you haven't, that's fine. Here's the idea. You have an integral, right? The integral of little f of x from a to b. What many of us have already learned is, oh, okay, I know how to solve this. You give me two numbers here in a and b, right? I solve this by doing the antiderivative of little f, which we often call big F. So the antiderivative. Anti, you just think of meaning opposite, right? So take the antiderivative, plug in b minus plug in a. We're going to use this over and over and over again in this course still. You've already used it in Calc 1, we're going to use it again. But this is kind of a very important piece that we're going to start off having to remember. And so let's just kind of get an example of this going in here. So, let me pick a nice little color to start. Purple's my favorite, so we're going to use a lot of purple. So what's an example of this that you might have seen? Well, let's do the integral from 1 to 2, okay, and what function? There's maybe some of you have gone kind of deep into this and seen the many functions and their antiderivatives. We'll do a couple examples here. Maybe you haven't seen too many. So let's start with x squared dx. Okay, so how do I solve this integral? Well, the evaluation theorem says, oh, it's nothing. You just figure out, okay, what's the function big F? So this is the function I'm looking for here. What is this big F of x such that when I do the derivative of this, I get to x squared? So it's setting up a formula and you're asking, well, what's the function I have to plug in so that when I do a derivative, I get to x squared? Right? So this is how we're going to, think of some of these integrals that we need to learn how to solve. This is one way to do it, is to just go backwards. Like, oh, we remember derivatives. Well, an integral uses the antiderivative. So just, you go backwards. So, okay, I need to start with a function. When I take its derivative, I get to x squared, right? So if we remember how these powers work, right? What function do I need to start? What power up here gets me down to a 2 power here, right? And this is doing the derivative. Well, if I remember correctly, this has to be a 3, because what does the derivative do to the power? The derivative, remember, drops it down 1, right? 3 minus 1 is 2. So that's just trying to remind you of some of these derivative ideas. But then we have to remember, okay, well, that's not the whole process, right? What was the whole process? Well, the whole process was what? We took the number up here, right? The 3. Drop it in front. Then subtract 1. All right, so that's derivative. X cubed gets to this. Okay. But we're close. We've got this x squared. Hooray. We're feeling pretty good. But we've got this 3 here. And if I go down here, I don't see a 3. So what are we going to do? Well, I want to not have that 3 being multiplied. So I got to figure out something to put in at the start here that will cancel with this 3. I've got this 3 at the end. I don't want this. How could I get rid of this? Well, it's being multiplied, right? So what's the opposite of that? Divide. If I had a 3 on the bottom here, these would cancel, and I would just be left with x squared. Right? Because they would cancel the 1. Mathematicians are lazy. 1 times a number, it's just that number. Don't write the 1 anymore. So I just need some 3 on the bottom here. Well, you might think like, well, okay, well, how do you do that? Well, just do it, right? So what if I do this? Start with this function. take the derivative. Just practice. Take the derivative. Drop the 3 down. Oop, that's 3 over 3. Good. Subtract 1 up here, x squared. Okay, well, there you go. The 3's cancel. You're left with x squared. So this is equal to 1/3 x cubed. And then notation that, again, this might have been a while since you've done this. The notation we use when we're using this theorem before we plug in is we draw this vertical line here, and we put our a and we put our b here. And this is telling us, once we have this vertical line, I've done the antiderivative. Stop with the antiderivatives. All that is left is to plug in. Okay? So then you just do it using this theorem. Take b first, that's the top number, plug it in. So 1/3 2 cubed, because I'm plugging the 2 in here, minus 1/3, okay, and then 1 cubed. That's the evaluation theorem, right? You take the antiderivative, which, remember, we have rules for this. Just kind of trying to remind you how we kind of thought through some of these rules. But there are rules for doing these integrals. And so I'll remind you of what this rule is for x squared. And we'll learn more rules for more functions as we go through, right? But, that's the whole idea. You take the antiderivative, which was just answering this question. What function, when I take its derivative, gets to x squared? We found that was 1/3 x cubed. And then you plug the bounds in and subtract between them. Okay, so let's do that out. That's 8/3 minus 1/3, which is 7/3. Boom. All right, so just to remind you, evaluation theorem. You got to get your antiderivative, you're going to plug in. Boom, done. Okay, and so, this is something that you might have to review. You might have to go back and do a little review of, is thinking through all these antiderivatives. So, just to kind of remind you of a couple of them that are more common, right? So if we have some function here, f of x, and then we want to also talk about the antiderivative, big F of x. This is the antiderivative. It's the go backwards, right? Okay, well, we just did this example, x to the n. Now, can you look at this, and this is an important thing to be able to do when you're in a math class and you're thinking about these things, and you're trying to find the new pattern. Well, what did we do? We went 2 to 3, okay? 2 to 3, so that's add 1 to the power. And then what did we do? This 3 actually popped up again, right, on the bottom. So that would be divide by n plus 1. And here you go. That's our antiderivative rule. Add 1 to the power, divide by that number. Boom. Now, you got to be a little careful here. Like remember when we were doing derivatives, x to the power n, we were just, oh, this is no problem. Great, great, great. Except for, we do have one issue here. And the one issue is we're dividing by a number. So we've really got to make sure that number's not 0. But it could be, right? Think about this. N plus 1 could be 0 if n is negative 1. And this isn't going to make any sense, right? If I try this, I'm going to get 1 over 0. That doesn't make any sense. So this only is true. So this like little kind of, pattern we found here, this formula, is only true. So this line is true if n is not negative 1. If n's negative 1, we need something else. It doesn't work. But if n is not negative 1, we're good here. So some other ones that we want to remember, we've got cosine and sine. These are, very common for us to go through, right? And so we just got to remember what function, when I take the derivative, that's this, when I take the derivative, do I get cosine out? That's sine. When I do the derivative of sine, I get cosine. Okay? Well, what function do I take the derivative of to get sine? Well, remember, they just go back and forth. Except The derivative of cosine is negative sine. So this is an example kind of like of above where I've got to throw that additional negative in to counterbalance because I don't have a negative here. What gets rid of a negative? Another negative. There's a few other ones that, we can kind of go through. For example, secant squared and tangent. So the derivative of tan is secant squared. So then I know the antiderivative of secant squared, it's tan, right? I can kind of go back and forth here. And there's some more that you might have played with when you learned about antiderivatives the first time. And we're going to just spend a good amount of this course adding to this list of functions we can find the antiderivative of. But these are a couple that are pretty useful to have in your back pocket as we go through. So, that's the evaluation theorem. You give me a function in an integral here. It's not too bad. I find the antiderivative. I plug the bounds in. Boom. Good to go. All right. So we need that for the fundamental theorem of calculus. This is very important. So let's go down and get to this fundamental theorem. And so the way that this is going to work, this document's going to work, is I'm going to take pieces of the book. So this is in the book, and I'm going to show you how one can go through it. All right, and so talk it over, kind of think it through, but this is trying to get you to see a model of what it's like to read something like this, because there is a lot of information packed in here. So let's just read this first thing. We'll read it once through, and then we'll dig in. The fundamental theorem of calculus, part 1, if f is continuous on some interval a to b. Remember, a to b are just numbers, right? Every time you see this, you should just think numbers. Then the function g, defined by g of x, is an integral from a, again, a number, to x. This is no longer a number, it's now a variable, so keep that in mind, of f of t dt, is defined between a and b. So telling you where the domain of this function is, right? This is telling me where can I even do this, which is connected up here. So it's defined by that integral. That is actually an antiderivative of f, and that is given here. The derivative of g is f on this domain here. So what are we saying here? Basically what we're saying is, look what I can do. I can make a new function out of an integral. Create a whole new function, g of x here, right? By basically accumulating this f of t. This is sometimes called an accumulation function. And the way you can think of this, it's pretty interesting the way this works, is you can think of this f of t function as representing change. Often people like thinking speed, velocity. That's the kind of like common, how do I think about this in real terms? Okay. So if you think of this function f as your speed, like be in a car or running, whatever you want to do, however you want to transport yourself. So if this function somehow is showing you speed, then how do I take that and get something useful out of it in terms of where I am, right? I know how a car is moving over some time period. So what? What does that tell me? Well, this theorem is telling you that if you know how a car is changing speed over time, you can actually construct its position over time. That's what this theorem says. It's really, it seems on the face of it like it's like, oh yeah, sure. It's really a fundamental, I mean, it says fundamental in the name, right? So I guess I'm not giving you anything new. But it's really a very deep idea. Really think about what this means. Knowing how something changes over time, this construction gives us a way to perfectly, out of that information, construct where the thing is over time. That's just this one example of how x, t, g, and f are working. We can think of other ways and scenarios in life where we could apply this, and it's still just as useful. But for now, just the change in speed. how something changes if I only, think about this, I'm only focusing on the change of something. I can construct the state of that thing only with its change. That's what this is saying. This is an immensely powerful idea. Just accumulating change. Oh, you changed a little bit more. Okay, let me add that in. You changed more. Let me add that in. You changed more. And let me add that in. I just have that information. I can construct and tell you a ton about that thing by only focusing on how did you change? How did you change? How did you change? That's what this is telling me. That's what this setup is. I'm going to, remember, integral, add up. That's a great way to think of the integral, is a way of kind of adding things. What are you adding? You're basically just adding the change. Add the change, add the change, add the change. I can now reconstruct a function that tells me about this thing that's changing by only focusing on the change itself. So, pretty crazy idea, actually, when you really dig into it. And that's really what the focus of this section is. And it's kind of got two pieces to it. We'll start with the first piece, which is really trying to dig into how this f and g play together. Because what you'll see is we often have f. We will often be given f as a function, a graph. And we'll want to be able to reconstruct g, learn about g, tell me everything you know about g. And you'll see we can actually know a ton about this function g just by looking at f. Not even calculating the integral necessarily, just looking at f. It's kind of crazy. You'll see kind of how deep we can go with this, right? And it's going to use the evaluation theorem. So I'm going to actually start you off with kind of a little crazier example here. So here's the function f of t is sine of pi times t squared over 2. So all this is done in Mathematica. You can have the Mathematica notebook. It'll be posted for you to play around with. So you have all that to mess around with, and that will be available. So, okay, let's stop and go like, all right, what's going on here? So we got a function, sine. You see how it's bouncing all up and down? That's sine-ish, but it doesn't look exactly like sine. That's what this t squared is doing in here, right? It's changing some stuff up, but it's bouncing like a sine curve kind of does. So, all right, okay, that's fine. It's a little bit weird, kind of looks symmetric. Okay, so those are some things you could just think of looking at this. So that's cool. But, you know, how does this connect to this theorem we just talked about, right? Because this is the whole point. Well, what we can do is we can define a new function, g of x, by taking the integral of this function, this picture here, over a certain range, okay? So let's think about this, and let's write this down. Or maybe we'll do it down here. So what are we saying here? So we're saying g of x is going to be the integral. Now, before I even write any more, here is a helpful tidbit in all of your future math courses and everything. You get a theorem like this. I know I picked a kind of a little bit more confusing function here to start with. But whenever you're first trying to understand something like this, make it as simple as possible. So what do I mean by that? Look at the way this is defined. I'm doing g of x from a number, up to x, and I'm going to change x. What's the simplest a I could pick so I don't really have to think, too crazy about this? Right? What's a simple a I could pick to try to hopefully make this easier on myself? Well, one way to do this is 0. Let's let a be 0. So just off to the side here. I'm going to let a be 0 for this first example because I want to just try to make as many things simple as I can while I'm understanding an idea. We are then going to let our upper bound change. And I'll kind of, we'll do a couple example points so you can see what that looks like. And I'm going to integrate f of t. Again, this blue curve here is your f of t. So let's, we've got the technology. Let's get fancy here. Right, we've got the tech. We can do it. Boom. Made that blue. Hold your pause. It's fine. It's excellent. So we've got g of x is integrate this function from 0, here's 0, to some x value I give you. Because it's a function. I give you an x. you plug it into whatever you got to plug into, you spit out a number. That's what a function is. So that's what we need to be able to do with this. So I have down here a table. And what I want us to do is think through each of these. We're not going to do the calculation, just think through it, okay? So if x is 0, what is g of 0? Well, let's use the formula. It'd be the integral from 0 to 0 of f of t dt. So, you know, what does that mean? Well, go up to the picture. Here's 0. And what's a nice way of thinking about this when you have the picture? Remember, the integral from a to b, we like to think of as area under the curve, right? That's one way we talked about integrals. They're adding up this area. We're going to be a little careful, positive, negative, which we'll get to in this in a second. But you know, that's the general ideas. We're looking at this area under the curve. So what's this integral say? It says, give me the area under this curve from 0 to 0. So I start at 0, and I go travel to the upper bound here, and I count up all the area. So here I go. Ready? I'm at 0. I got to get to 0. Did you miss it? I think you might have missed it. Let me do it again. Did you miss it again? Oh, I didn't go anywhere. You're right. I didn't go anywhere. It's 0 to 0. I didn't move. So there is no area under this curve. So what did we just learn? This function I've created, when I plug 0 in, I get 0. So I know a specific point on this curve g of x. I could draw it. It is 0, 0. Hits that point. And we're actually going to do this later, is we are going to take a function f of t and try to construct this picture by just looking at this function. It's insane, I know, sounding, but we're going to do it. So this first point's 0. Okay, well, let's get to a not silly point. Let's plug in 1. So I want to know, what in the world is g of 1? Well, plug it in. 0, now 1 goes up here. And let's see what this looks like. So I go back to the picture here. Okay, so here's 1. All right. What do I want? Remember, integral, area under the curve from 0 to 1. So I'm going to try my best to draw a nice vertical line here. Nailed it. And then I want all this area. Okay. So, you know, this isn't set up super nicely to kind of figure out what this is just looking at it, because it's a curve, not a straight line. There's no geometric shape we could really use here. So, you know, that's a little tough, but we can learn about it, right? We can think through this. First things first, what can I say about this? This area is above the axis. So I know g of 1 is a positive number. I know it's bigger than 0 because there's some area. I know it's a positive number. Okay? What else could you say? I mean, you know, this is not something you necessarily have to go too crazy with, but you should always be just stopping and thinking about what you're seeing, just as much as you can say. So what's another thing I could say? Well, check this out. This is a 1 by 1 box. See how it's 1 with 1 height. Not to scale, but it's still a 1 by 1 box. The area of this box is 1. Guesstimate. It kind of looks like maybe I take up about half of the area of the box. So just guesstimating, it looks like from this picture, just again a guesstimation, we can actually do the calculation. A guesstimation, it looks like this is, let's see here, it looks like g of 1 is about a half. Right? So, because it looks like maybe that purple shaded curve fits in about half that box. Okay, so, all right, great. So we think it's about 1. All right? We're going to go over to Mathematica and actually calculate these in a second using the integral. Because we actually haven't talked about, like, how do I actually integrate this thing? So don't worry about that right now. All right, but then, you know, let's think about g of 2. So let's check out g of 2. And just, again, we're just trying to think through. So this is the integral from 0 to 2 of our function above, f of t dt. So let's go check it out. All right, so let's change up the color a minute. Let's maybe go green here. So again, I want to start at 0, okay, and then I want to go out to 2. So I want all the area under this curve. So, what's happening here? I get the purple, but then I also get, so how do we want to do this? We'll do all of this area in green. So green, green, green. All of this is green. But then I also pick up all of this green. Ooh. Okay. So this is now G of 2 is all of this green. So we got to be careful, right? Because remember, when we think of these as areas, if the area is up here above the axis, it's positive. If the area that we're calculating is down here, it actually counts as negative. So what we have to think through is like, okay, well, what is G of 2 going to be? It's going to be this green, and then that's all positive, this area, and then we're going to take away this green. So, oh, goodness, like what is that going to be exactly? That's a little tough to say, but just eyeballing it, it does seem like this green area that's negative, that's being taken away, is smaller than this. So just kind of checking this out, I do think G of 2 will be a negative number. But it's quite hard with this to actually tell exactly what it's going to be, right? So this is pretty tough. Maybe you want to go give it a guess at what this is, but at least I know it's positive, right? Just because this negative area is smaller than this one. You could take a couple guesses to say to yourself, like, ooh, do I think when I take this whole green and subtract this, is this going to be bigger or smaller than the purple? I think it's a little tough to say, but you could take a stab at that, see if you can figure it out. But we're just going to go to Mathematica because this function's a little tough and have it calculate for us. So we're not really sure how to compare it to 1/2. But that's the process. That's it. You give me an x. All I do is I start at my a, which is 0 in this case, every time. See how I started at 0 every time for these? That a doesn't change in a problem. It just gets fixed. That's always your start point. Then you give me the x, I plug it up here, and that's where I go to. 0, 1, 2. I could go out further. I could go the other way too. I could go to -1 to -2, and we could do that as well. We'd have to think through it a little bit, but we can do it. And so that's it. That's the process. That's how you would construct the values of G. Okay. What we're going to do in a little bit is we're going to go a little deeper and say, oh yeah, that's cool and all, but it's especially with these functions that are a little tougher. It's not really very rigorous. Like, can I do a little bit better here? Like, how do I learn more about G? G's a function. So think back to Calc 1. What can we learn about G? We can learn where it's positive, where it's negative, where it's concave up, where it's concave down, where are the local maximums, all of that kind of stuff. We could learn about a function just using derivatives. G's a function, so I should be able to learn all those things just by looking at derivatives. We're going to be able to do that. But first we need to start with, how do I even calculate G of 0, G of 1, G of 2? I look at areas under this curve, f of t here. So, and that's one section of problems I'm going to have you do some practice on, which you'll see down here. Skip down this for just a second. So here is a very typical type of example to try to use, okay? So I've given you a function f, right? Here's its graph, right? I'm asking you find values of g. Remember, what is g? G is the function defined by taking this graph and finding areas under the curve. Remember, g is the antiderivative. F is the derivative. I'm going to keep saying that over and over again here, right? This is the antiderivative, and this is the derivative. So we just have to keep reminding ourselves that if I take the derivative of g of x, I get f of x. Okay, that's a very important piece, right? Go back up to the theorem. Keep going back up to the theorem. Remind yourself, g prime of x is f of x. This is not written here just for fun. It's a useful thing to be reminding. This is critical to keep reminding yourself of. Okay, this connection. Okay, so, all right, how do I do something like this? Well, it's just like we did before, right? So there's a solution down there that we'll look through, but just kind of quickly to do one together. Let me switch back to purple here. So it says find G0, G1, G2, G3, G4, G5, and then sketch a rough graph of G, which we'll do together. So G of 0. Well, how do I do that? Well, just plug into the integral. That's always your first step, especially when you're first kind of feeling this out. So it's the area between 0 and let me go to 0. Insert the joke about you missing it again. 0. Okay, so what do I know? I know when I plug 0 into this function g, I get 0 out. So, you actually could just kind of immediately start this off, right? Let's draw this out. Let's go x, and then here we're going to draw out, this g of x here. Okay, so 0, 0, boom, right? Because when I plug 0 and I get 0. All right, so I'll call this y equals g of x. So, okay, what about g of 1? Well, just plug it into the integral, add up all the area from 0 to 1. Okay, so let's do it. Here's 1. Oh, okay, so, I get a little triangle here. That's pretty neat. So I know how to calculate the area of a triangle. It's 1/2 base, see the width of 1 here, base, times height, 2. So there you go. The area of this triangle is 1. So that, what does that mean? When I plug in the number 1, I get up to 1 here. So my function g starts here, hits here. Okay? So that's g of 1 is 1. So I know that those are 2 points. All right. G of 2, let's do that one. Again, 0 to 2, f of t dt. So let's do this let's do a light blue here. Oh, light blue that's silly. That's the color of the function. So, okay, so this g of 2 now, go here. So I want the area from 0 to 2. Okay, so that means I get the purple plus I get this new stuff. So this new area plus what I've already done, because remember it's 0 to 2. So one way that's really nice to do this, that's kind of neat, is if you think about this, g of 2 is really g of 1 plus this extra green. So let me write that out. G of 2 is equal to g of 1 plus this extra green shaded region that's in the picture. So this is kind of neat because you already know g of 1 is 1. So okay, great. This area was 1. So all we have to do is figure out this area here. Well, this is a rectangle, base 1, height 2. So this is area 2. So then this is going to be 1 from g of 1 plus 2 from that green shaded region. All right, so let's draw that on here. When I go to 2 now, I get 3. 1, 2, 3. So we'll put that as our little green dot. There we go. All right. And then we just keep going and we can kind of see what happens here. So when I go now and do g of 3, right, I insert, we can do that in maybe like a little red. This doesn't really look red to me, but maybe it'll be different in the video. G of 3, I guess that's right, is the integral from 0 to 3 of f of t dt. So let's look at g of 3 now. So this is the area under the curve from 0 to 3 of the function f of t, right? So we already actually have some of this done. So really all we need to add to this is just this area here between 2 and 3. right? So what we're going to do here is we're going to take g of 2 and add in this extra area. So then let me just write that out, and I'll try to color code this too. So this is going to be equal to g of 2, okay, and then plus this extra area here that we need to grab colored in. Now in this problem, this function is you know, who knows, maybe it looks like it's a cubic or something like that. And from a picture like this, it's difficult to see, right? So let me just zoom in here so we can even see a little bit better exactly what's happening with this function. Well, that was not the zoom I wanted. There we go. So it's got this curve to it, so we're just going to approximate it with a triangle. You know, this is not about being super precise here. We're just going to, you know, try approximating with a triangle here. So actually it's going to be the same as this triangle, kind of cutting here, height 2, base 1, and so that will have an area of 1. So that'll be 1. What was g of 2? G of 2 was 3. So altogether, this is going to be, that's a 3. We'll say that g of 3 is approximately 4. Okay, so if we went up one more here on our little picture that we threw together, once we hit 3 now, we're up here at about 4, and that's where our picture will go, or our little point will go. So we're up here at 4. Okay, so not too bad. Now here's where the interesting stuff happens. Not that that wasn't interesting, but you know. So when we now go to 4, g of 4, it's going to get a little weird because we are now adding in this negative area, okay? And so negative area, what does that mean? Well, so we could still think of this as area under the curve, but since it's below the axis, remember that accumulates as a negative. So we still, to calculate it, g of 4, we want to just plug into the formula. 0 to 4 f of t dt, okay? But remember, we've already, this is an accumulation, so we've already accumulated this first chunk of area. So this is going to be approximately, and I'm just bringing this 4 down here, we'll even keep color coding it. It's going to be about 4 here, and then we're going to have minus the shaded area here. Again, minus because it's below the axis. And so again, this is curved, so we're not really sure exactly what it is. And we could probably figure out what this formula might be, or something close to it. But we're just going to use a triangle again here just to see. So using a triangle here, it's the same as this one. It's got 2 is the height, 1 is the base. So we'll just call that minus 1. So minus 1. And that's going to, again, be about 3. Okay, so that's g of 4. So it's gone down now, and let's color that in over here, back down to 3. So kind of looking through this, you know, we're going to go back and forth the connection between these two graphs in a second. We'll finish g of 5, and then we'll get there. So g of 5, let's see, I might be running out of colors here. Let's see, we could do gray. g of 5 is the integral from 0 to 5 f of t dt, which is just, again, accumulating all this area, or the negative, but then adding this extra bit. So we're going to then end up with 3 from the previous. All right, it's going to be equal to 3 from the previous. And then again, it's going to be this minus this gray shaded area, which, looking at it again, about 1 again. Well, you know, we're not 100% here, but as an approximation, this should be fine. And so I should say approximately. Okay, and so that's going to be equal to that, which is equal to 2. And so if I went out to 5, I'd be at about here. Okay, so you see my points. All right, so kind of some of the connections we should make here. Remember, this is a graph of the derivative. This is a graph of the function. So a couple things we got to remember from Calc 1. When the derivative is positive, the value of the derivative is positive. See how this whole blue is above the axis? That's positive. What does that mean? That means that the function's increasing. So watch this. This is positive right after 0 up until 3. Watch what's happening to the function. Increasing, increasing, increasing. Hits 3. Okay, then what happens? Well, the derivative is negative, so I should be going down again. Boom. So that connection that we learned in Calc 1 between a function and its derivative still applies here. Massively important to remember. Function, derivative. What's the derivative? Tell you about the function. What's the second derivative? Tell you about the function. Okay, so we got to try to remember how that works. But there you go. Not too bad to try to do that out. Okay, let's zoom back out now. Got a little solution here. You can kind of see how they did that. All right, next example. So this example is using the other part of the fundamental theorem. And that other part is specifically trying to calculate the derivative. Now, what do we just see here? You gotta think about what I just said with this one. See how we define this? G of x is the integral from 0 to x of f of t. This f of t is the derivative of g of x. So, okay, hold that in your head. Let's go back down here. This f of t is the derivative of g of x. All right, I'm pausing for dramatic effect. So let's see if the effect has taken hold. Okay, so g of x is equal to the integral from 1 to x of f of t dt, but that's t squared dt. So find a formula for g of x and calculate g prime of x. Okay, well, let's actually just start with g prime of x. G prime, what's the derivative of this function? Sitting right here. Okay, so are you telling me it's just t squared? Well, this is a function of x, so we use x. But yep, that's it. Done. That's the derivative. Okay, but we can, we can actually also do this integral using the evaluation theorem here, which it shows. And we just have to remember that we're looking for the antiderivative. So to actually compute this integral, right, this step they take here is the antiderivative. Right, we're comfortable with derivatives. T cubed, how do I take the derivative of this? Right, I drop the 3 down, becomes a 2. Okay, cancels with the 3, I get t squared. So remember, derivative, antiderivative just go the other way. So they do that. They take the antiderivative, bring us back here. Then remember, you plug the bounds in. So x cubed over 3 minus 1 cubed over 3. That's how they got here. They just smushed it into one fraction. So I'll write that out for you. X cubed over 3 minus 1 cubed over 3. Same thing. Okay. All right, so then this is your g of x. That's the formula, closed form formula for this function defined by an integral. Sometimes it just has a nice formula, and we can calculate that. All right. What's the derivative? Well, the derivative of this is x squared. I told you that. Because when I define a function this way, from a to x, this is important, then this inside function is just the derivative. That's pretty much the whole point of setting it up this way. We are using the integral to accumulate this change. You think of derivative as change. So this is changing, and we're accumulating. We're grabbing all up the change. Sometimes it's positive, sometimes it's negative, but we're grabbing it all, grabbing it all, grabbing it all. We're accumulating it, and then that's going to help us find this g of x. So there you go. So the derivative of this, not too bad. Okay, so let's go back to our example of sine pi t squared over 2. All right, so remember how we had set this up before. We have a function g of x, which was the integral from 0 to x of f of t dt, okay, where f is this function, which is graphed below. And so we might want to ask the question, well, where is, based on this, where's g going up? When's it going down? When's it concave up? When's it concave down? And so what you need to do is remind yourself of the connection, right? And it's okay to just keep writing this out for yourself, however you need to do it, right? So let's see here. So remember the general connection here, although I'm going to write it in terms of these functions, right? G of x is increasing when its derivative, g prime of x, is positive. So that's the connection there. G of x is decreasing when its derivative is negative. But remember, this is f, right? The function f is actually the derivative. So what we really need to be doing is looking at this picture. If we want to know what g's doing, increase, decrease, we just need to look where is it positive and where is it negative. And so you just, just to kind of see this, well, let's just look at the picture. So the picture here, we're looking at this picture, and I'll just do a little shading. So could I have picked a worse color for that? I think not. Let's pick pink here. Okay, I'm going to shade where g, the function's increasing. All of this, all the time here. G, the function g is increasing. And not there, but all of this, I'm increasing if I'm g. If I'm g, I'm increasing. Not anymore. And here, I'm increasing. So all this pink area, I'm increasing. And then on the other hand, though, g, the function g, I'm going to be decreasing when this graph is negative, has negative values. So that's down here and down here. Whee! Not there. And here. Woohoo! All of me. And then here. Okay, so g, again, this is f, but the function g right here is increasing throughout this whole pink zone, and it's decreasing wherever I drew green. So amazing. We can get all that information just from that. Now, how would we actually kind of try to figure this out, to be more specific? Because I just drew on this picture. I didn't actually tell you values, right? If we're looking at this, this is saying I'm increasing from whatever that point is up to 0, and then also 0, not including 0, to whatever this point is. What the heck point is that, right? Well, this is our function, so let's rewrite it down below. Sine pi t squared over 2. So let's just rewrite this. What are we actually trying to do here? We'll start with increasing. We want to know when sine pi t squared over 2 is positive. That's what we're looking for here. Okay, and so, it's okay. You got to write out a little circle here. Remind yourself. Sine, remember, is positive between 0, right? So it's actually, 0 at that point, but not included. 0 up to pi. This whole range, not including the 2 points, 0 and pi, we're going to be positive. Okay, so, but be careful here, right? That's just regular old sine, right? So sine of theta is going to be positive when theta is between 0 and pi. Okay, but we don't have theta, just a regular old theta. We have pi t squared over 2. So we need to figure out when that's happening. So just move some stuff around. Multiply by 2, divide by pi. That's going to give us 0 less than t squared. and then that'll be 2 pi, but then you actually divided the pi, just leaving 2. So that'll be 2 over there. Ran out of room, so that's okay. Then we're looking for all the t values between where, when you square them, you're between 0 and 2. Okay? So we have to think a little bit about what that means, right? So let's just take the kind of first approach at this, the kind of naive first thing, is you might just kind of try to square root this. So that would put you here. Okay, now we can think through what square root of 2 is, but what you'll end up noticing is that that puts you actually right about square root 2 right here. So, okay, 0 to root 2. Boom. That's that one. Okay, but remember, this was like your, and I'm not saying you specifically. You might not have fallen to this, but I fall for this sometimes. This like naive, just do the square root and oh, look at me, right? But then we also have to remember that, you know, you can't just square root a square every time and everything's golden, right? Because also the way this works when we do this, when we have this inequality, is that t between 0 and negative root 2 also works for this, right? That's why this one's all lit up, okay? So this is also true, right? This little grouping. Okay, and so then, you know, you've got some more work to do because this repeats, right? Because it's 0 to pi, I'm going to be positive if I'm sine. But then remember, this keeps happening. So it's boom, 0 to pi. And then I would be negative here on sine. I'm negative for some of these sine values next. But then remember what happens. Look what happens. I'm back positive because this axis here is me just going woo, 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 woo around this circle. And so this function really goes forever. I only decided to draw it from negative 2.5 to 2.5 as a t value. But remember, this keeps going. So that's just something to kind of try to, you know, keep in your mind a little bit when you're going through here, is that this function, it's sine, so it's going to continue to, you know, run around the circle and copy and copy and copy, okay? So, you know, that's that first chunk here that we're looking for. So I'm doing this all by hand. Now, what actually happens when we go back around the circle? Because I want to do this one more time. So just to kind of show you what this looks like, and then we're going to do it in Mathematica so you can get a feeling for what it looks like to do it there. But this is also true, right, between 2 pi and 3 pi. So also, sine theta is greater than 0, right, when theta is in between 2 pi and 3 pi. But remember, we have pi t squared over 2, right? Again, start stripping all this away, right? You get a 4, the pi's cancel, so you're going to get 4 less than t squared less than 6, and then you're going to, maybe naively, but it's okay to just kind of off the bat square root just to see what should happen. So you're going to get 2 less than t less than root 6. Okay? And as you can see, look, perfect, 2. I'm going to be increasing up to root 6. Now, what's pretty interesting here is you might have expected this range to have just kind of continued, this range of increasing, the same thickness, the same picture, to kind of just keep going. But because of this square piece, right, as we move out in t's, this stretch of us increasing is actually getting smaller. So this is getting smaller, which is kind of cool, right? And so it's because of the square and having to do the square root, we're actually shrinking that. Right? And so this might be something fun. You can go into Mathematica and try to stretch this out and see what happens to the function. And then also flip this onto the other side, right? And, right, it's the same thing over here. it's going to be at -2, -√6 is that other positive. So that's those two. So each time I try to solve this, each half circle I run gives me a positive and a negative range of increasing. So this was a half circle, and this was that same half circle, 0 to pi. Then this was 2 pi to 3 pi, but so is this. Okay, and so, you know, let's get rid of this because we need a lot more space. When are we increasing, decreasing, to be more specific? I mean, this is a little bit harder to kind of just do out, but what we can do is on the range -2.5 to 2.5. We're just going to stick here. G of x was increasing, so G of x is increasing between 0, 0 and √2, between -√2 and 0, also between 2 and √6, and also between -√6 and -2. So it's all of those places it's increasing, and so it's just going to be decreasing everywhere else. So this is kind of nice to do. You can just, you know, go everywhere else to see decreasing. This one would be √2 to 2, union, and then let's see, this is going to be, here was √6, and then we just stopped at 2.5. Although, of course, this function keeps going forever, so we could keep figuring out what this looks like, but we'll just stop there. But then on the left, what happened? It was between -√2 and -2, -√2 and -2, and then also, what was this other one? -√6 and -2.5. Okay. Boom. And then to the end. So there you go. Intervals of increase, decrease. All right, so the last thing in this section is talking about some more general scenarios with these functions, because you don't just have to have an x here, right? You can have any, you know, almost anything you want. So what about this function? H of x is defined to be the integral from 0 to x squared, not just x now, of this derivative function. You can almost kind of think of it. All right, so fundamental theorem. Well, the fundamental theorem, if you're just trying to blindly use it, just makes you think that this should just be, oh, this is easy, right? Woohoo, look at me go. I'll just plug in an x. Hooray! Now this is wrong, and the reason it's wrong is because we're thinking about the function wrong. So I'm going to have you rewrite this and think about this in a different way. H of x is really the combination of two functions. So let me give you an idea of what I'm thinking here. G of x I'm going to define as this function, and you're about to just look at me and be like, what the heck are you doing? But think about this for a second. G of x is the integral of the same inside from 0 to x. So what's G prime? Well, the fundamental theorem just immediately applied tells us it's this. So, okay, sweet. But H of x then would be G of x squared. See how I'm now writing this as a composition? This x squared would get plugged in, go up top, and boom, that's H of x. So, okay, what's the derivative then? Well, the derivative of H prime, this is chain rule, right? This is equal to G prime of x squared times the derivative of x squared. But I know G prime, right? Fundamental theorem tells me it's this. So that's 1 plus, now instead of x cubed, right, I don't plug in x, I plug in this x squared. Boom, times 2x. Which, of course, you can, you know, rearrange if you want, try to write it a little bit nicer. There you go. That's my derivative. So, chain rule. big important piece. If you see this is not just x, you're going to use the chain rule. But if you think of h as a composition of functions, then it's really not too bad to kind of go through this chain rule. So let's try another one. So two messed up things here. Not only is this not just an x, but it's also on the bottom. That has a pretty quick fix though, because when going through here, you just got to remember, I can rewrite this integral by putting a negative sign in front. I can flip, boom. Easy peasy. So okay, and now that gets me into the piece above. So the piece above, remember, y is equal to g of e to the x, where g of x, and you can call this whatever you want. I just picked g for Gary, I guess. G of x is the integral, right? So I should put a negative in here. 0 to x sine cubed t dt, which the fundamental theorem tells us, because it's in the right form, that's going to be negative sine cubed x. Right? Because the fundamental theorem tells me just immediately, just plug the x in, you're all done. So y prime will be g prime of e to the x times, what's the derivative of e to the x? Because again, chain rule, that's e to the x. Okay, so g prime is negative sine cubed, but I don't plug x in, right? I plug e to the x times e to the x. Ta-da! These really aren't very bad. You just have to look at the problem and approach it as like, oh, wait. Like I've said in other videos, other things before, or I will say in the future, all of these problems that look more complicated, right, are just easier problems lumped together. So you've got to start approaching these as, how do I simplify this into an easier problem? Maybe a couple small easier problems. And what you notice is, once you've kind of seen the tricks of this, you can swap these with a negative, and then, oh yeah, this is just one easy function, which just immediately I can get the derivative of using the fundamental theorem, and it's composed with e to the x, which is actually also another easy function. Now I've got that, I just apply the chain rule and I'm all done.